Hey everybody, Mr. Grove here. Today we're going to talk a little bit about circular motion. And so circular motion is an object moving in a circular path, and compare that to rotational motion where an object is spinning around an internal axis. So something like a planet is doing both. So the planet is moving in the path of a circle around the sun, but at the same time it's doing rotational motion as it spins around the sun as well. So, but we're going to concentrate in this unit on circular motion. And so what causes the circular motion is the centripetal force. And so that is a force that acts towards the center of a circle. So this would be a centripetal force that is caused by the string. Now, a common mistake is to call a force a centrifugal force, because we use the term centrifuge a lot in circular motion, but there really isn't a centrifugal force that causes circular motion. It's always a centripetal force or a lack of centripetal force. And if we have force, a net force in a direction, then that means we're going to have a acceleration in that same direction. And so the centripetal acceleration will be towards the center of the circle. And so our formulas that we're going to use for this unit is going to be centripetal acceleration equals the velocity squared over r. And then if we take F equals ma, so centripetal force equals mass times the velocity squared over r. And that those will be our two main ones. We'll also use velocity critical equals the square root of radius times gravity, but that will come a little bit later. So let's work a first example here. If we have a plane that's traveling at 400 meters per second, it pulls out of a circular dive with a radius of curvature of 5,000 meters, so 5 kilometers. So our plane, our radius would kind of be this, and that would be 5 kilometers. And we know we are traveling at 400 meters per second. So we'll use our formula. So the centripetal acceleration is equal to our velocity, 400 meters per second squared. And that whole thing is squared. And then divide that by our radius, which in this case would be 5 kilometers. But if my velocity is 400 meters per second, and my radius is in kilometers, that means I got to get them consistent. So let's change that to meters. So that would be 5,000 meters. So my centripetal acceleration for that should work out to be 32 meters per second squared. And so that will be our centripetal acceleration. Now the second thing is how many G's is that? And we'll use this term G as kind of a gravitational thing. You know, fighter pilots, NASA will use the term G's, roller coasters. And so 1 G is equal to normal gravity, so 9.8 meters per second squared. So if we want to know how many G's 32 meters per second squared would be, we'll just put that in a ratio, cross multiply and divide, and we should come up with 3.27 G's. So that is how you would do that. Another one that we learned today is level curves. So if we have a curve on our road and our car is driving down the road, so we've got a 400 kilogram car, makes a level curve. The radius of the curve is going to be 180 meters. And the mu value between the road and the tires would be 0.8. And we want to know what's the velocity that we can take that at. So our formula that we would use would be centripetal force equals mv squared over r. We just have to decide, well, what's the centripetal force? What's causing us to make that curve? And sometimes it's easier to think, well, what if we don't have it, why do we slide off? Well, and that would be, in this case, friction. So if we don't have enough friction that makes the curve, then our car would slide off the road. So our centripetal force is going to be the friction, so force of friction equals mv squared over r. So if we look at it from, this is kind of a bird's eye view, but from a level view, and we take our car, we'll see that the force normal is going to be equal to the force weight. And so since friction is force normal times mu, and that would be equal to mv squared over r. And then that would be, we know force normal equals force weight. So weight, we know, was mass times gravity. So we would have our 400 kilograms times gravity, 9.8, times our mu of 0.8 equals our 400 kilograms, m, times our v squared, we don't know, over the radius was 180 meters. Okay, so we have to be in kilograms since newtons are a defined unit. And if you notice what's going on here is we have a mass on each side, so those will drop out. So when we're left with our answer, after we crunch it through, we get 37.6 meters per second. So that'd be our velocity. So if we try and go faster than that, the friction that we have is not enough to keep us on the road. Okay, so that would be our maximum velocity on this particular curve. Now, sometimes we don't have enough space. You know, if you're a civil engineer, you might not have enough space to make your curve bigger so that your velocity will get faster. And so what we need to do is bank the curve. And so this is pretty common. In fact, I challenge you to carefully take notice when you're driving around a curve, and you will see it's probably banked. At the extreme of this, NASCAR and racetracks will often bank their curves extremely much. So, I mean, 20, 24, 30 degrees sometimes. So in this case, if we have a banked curve, so as our car's driving around, we're looking kind of on it. Okay, and we would have our force of weight going straight down. And then we would have our force weight y. And then our force weight x. But we would also, the friction we know was going towards the center of the circle to keep us in the circle, and then we know force normal is going to be perpendicular to our surfaces in contact. So here's our surface, so perpendicular to that. So in this case, we have two things pointing towards the center that cause our centripetal motion. So force weight x plus force friction equals our mv squared over r. So we'll have to kind of go through our force weight. So we know force weight would be 400 kilograms times 9.8. So that would work out to be 3920 newtons. And then if we want force weight y, we would have to take the cosine 12 of our 3920, and that would give us 3834 newtons. And then our force weight x is going to be the sine 12 times our 3920, and that gives us 815 newtons. So now we can start to put stuff up here. We know force weight X was 815 newtons. We know our force friction is our normal, which normal is the same as weight Y here. So that would be our 3834 times our mu, which in the problem was 0.8. And then that's going to be equal to our 400 kilograms times our v squared over our r, which was the same radius, 180 meters. So let's crunch it through. 3834 times 0.8 plus 815 times 180 divided by 400, and square root that, and we get roughly 41.8. So we can take that curve faster because we've banked it about 5 meters per second faster. That's about 10 miles an hour faster. And so that's what we do. Now, typically, I don't encourage you to memorize force equations. We always kind of try to build our own based on the problem at hand. But in this case, I would say it's probably just a good idea to memorize on banked curve. It's the weight X plus friction equals mv squared over r. And then on level curves, it's the force of friction equals mv squared over r. So that's banked and level curves. Don't forget to smash that like button, and I hope that was helpful.